Hi everybody, thanks for being here today. My name is Ben Marshburn and I study marine science at Cal Poly in San Luis Obispo. And I'm really excited to talk to you guys about the research I've been doing this past 6 weeks. So my project is titled Burn to Bloom, assessing the impact of coastal wildfires on phytoplankton dynamics in California. So being a part of the terrestrial ecology group these last weeks, I've learned a lot about how wildfires are an intrinsic component of California ecosystems. However, due to managing practices and with climate change increasing temperatures and drought severity, we are seeing more wildfires and more severe wildfires, and those wildfires have a wide variety of different impacts, but today I'm going to specifically be talking to you guys about those impacts on the coastal ocean. So what's really interesting is there has been a lot of recent research done around this topic, specifically looking at phytoplankton and wildfires, as well as other effects of wildfires on the coast, like the turbidity of the water. And so with that in mind, I was curious about what aspects of wildfires specifically impact phytoplankton the most. And that leads me to my research question, which is how does normalized burn ratio, hydrologic connectivity, fire duration, and fire area in coastal California affect chlorophyll A, and can machine learning models predict these effects? So a really important tool that I utilize throughout my research is something called remote sensing. And remote sensing is the process of detecting information about the Earth via spaceborne or airborne instruments. And so how this works is those instruments are able to image solar radiation coming off from the Earth. And by analyzing those images, we are able to infer certain characteristics about the Earth's surface. And this can be multifaceted, so not only the land, but this can also be looking at the ocean as well. And so that's something, kind of like Megan mentioned earlier, that I've really enjoyed throughout my research, is that I haven't only been focused on just the land. I was able to connect the land and ocean and be able to study multiple things from each. And so first I'm going to talk to you guys a little bit about the ocean aspect of my research. And so phytoplankton are really important for our aquatic ecosystems and for our climate. They're primary producers, and so they photosynthesize and take light from the sun, as well as water and carbon dioxide, and convert that into oxygen and energy. And they actually produce over 50% of our world's oxygen supply. However, phytoplankton are not always good. This is an image of a harmful algal bloom, and harmful algal blooms happen when excess nutrient runoff comes into the ocean. And so these excess nutrients cause a large bloom in phytoplankton to occur, and when these phytoplankton die off, they strip the ocean of its oxygen content and can kill off fish. As well as there are certain species of phytoplankton that when they bloom, they produce toxins that are very harmful to marine life and humans as well. So chlorophyll A is a pigment in phytoplankton that absorbs sunlight during photosynthesis. And the reason why this is so important is because chlorophyll A absorbs sunlight in the red and the blue wavelengths, and it reflects sunlight in the green wavelengths. And we are able to see that. We are able to see that green ourselves, as well as from instruments mounted on planes, drones, and even satellites orbiting the Earth. So I use the moderate resolution imaging spectroradiometer on NASA's Aqua satellite to image chlorophyll concentrations up and down the California coast. So here, right here is an image of Northern California, specifically the San Francisco Bay Area, and in color you can see different concentrations of chlorophyll A along that coast. Each pixel represents about a 1 kilometer resolution, and you might also be wondering whether there's a lot of white space right here in the ocean, and that's most likely due to cloud coverage, which is a limiting factor in observing this chlorophyll A, is that MODIS can't see through clouds. And oftentimes there are clouds over the ocean, which can make it difficult to attain this data on the specific dates that you want. You kind of have to work with the weather that you're given. So now I'm going to discuss a little bit about the land aspect of my research. I use a program called Monitoring Trends in Burn Severity, or MTBS, which is ran through multiple different government agencies, including the USGS, and they use NASA's Landsat satellite to look at different aspects of wildfires across the country. So specifically, I looked at 9 different fires, 3 from the Northern California, 3 from Southern California, and 3 from Central California. And using MTBS, I was able to gather data on the fire area, fire duration, the burn boundary, and the fire severity. So with burn severity specifically, I looked at an index called normalized burn ratio, or NBR. And NBR is calculated by taking the short-wave infrared light and subtracting that from the near-infrared, and then dividing it by the sum of the two. And then from NBR, we can get something called difference NBR. And difference NBR, or change in NBR, is just subtracting the post-fire NBR from the pre-fire NBR. And right here is an image from MTBS showing the burn severity in the Southern California Thomas Fire. And from this key here, you can see how severely different areas of the fire burned. Another aspect I looked at was flow length. And the way I was able to calculate flow length was first acquiring a digital elevation model from NASA's Space Shuttle radar topography mission. And then from that digital elevation model, I was able to use ArcGIS to calculate a flow direction model right here. And then from the flow direction model, you can acquire a flow accumulation model. And a flow accumulation model basically just tells me where all that water is aggregating and accumulating and flowing. So you can kind of just think of it like a watershed map showing you where like the streams and rivers are in the area. And a lot of the fires only had one significant river, and so I measured that river's length. But for example, the Thomas Fire had multiple, I don't know if you can quite see it, but it has multiple rivers and streams in the area. And so I chose to measure the stream that ran through the most severely burned area of that fire. And so why is that important? So nutrients are absorbed along the riverbed and riverbank as water flows through the river. And I hypothesized that shorter streams are going to carry more ash and nutrients from those wildfires to the ocean, rather than the longer streams that are going to have that nutrients absorbed along the way. And so more nutrients leads to eutrophication, which is just the growth of phytoplankton. So I've talked to you guys a little bit about the data that I collected. Specifically, my input variables for my model were fire area, fire duration, stream length, fire severity, and the region of the fire. And I input that onto a model to try and see if I could predict the chlorophyll A concentration. I use a machine learning model called random forest regression. And basically how this model works is it takes my data and it splits it into a training set and a testing set. That training set is used to build a model which is made up of a multitude of different decision trees. Each tree is kind of just like a flowchart. Each node makes a specific decision based on a variable greater than or less than a certain value. And as you make your way to the bottom of the tree, you'll finally have your prediction, which is in my case was chlorophyll values. And then once you average all of those predictions from each tree, you get the total final prediction from the forest model. And then that test data that you split in the beginning is used to test the accuracy of the model. So here's some of our results from our model. My model had a moderate R-squared value of 0.36, which definitely shows a lot of promise in this research, and that there are most likely more variables to add on afterwards to make this model more accurate. Right here is a plot showing the actual values of the chlorophyll A versus the predicted values from the model. And something I noticed with these four values up here all had positive change, which just means that there was more chlorophyll after the fire than there was before the fire. And so 3 out of these 4 fires were from Southern California, the 4th being from Central California, whereas the Northern California fires and 2 out of the 3 Central California fires had negative change, meaning there was more chlorophyll in the water before the fire than after the fire. And one thought I had why this might be is just because Southern California and Northern California have different climates. Southern California is known to be hotter as well as receive less precipitation than Northern California. So that was one thought I had on why that may be. Right here is a figure showing the feature importances from my model. So basically the model deciding which variables were the most important in predicting those chlorophyll concentrations. And so region was the most important, followed by flow length and duration of fire. And so probably the most important thing that I've learned throughout my research here at SARP was that doing research, you often get a lot more questions than you do answers, and that's okay. So some of the things that I've thought about that I would love to continue working on is expanding my analysis. So not only looking at possibly more fires in the past, but also continuing to gather data on fires in the future, or in the present and in the future as well. And then also, like I mentioned, there is definitely a lot of room for improvement on my model's accuracy. So looking at more different types of variables and how they might affect the chlorophyll as well. So 2 variables I thought of were 2 other methods of nutrient transport, which were rain and wind. So for rain, like looking at maybe the mean precipitation throughout those fires, as well as possibly imaging the chlorophyll concentration off the coast after a significant rain event, because most likely that rain is going to bring nutrients and ash from those fires into the ocean. NASA also recently just launched the PACE satellite, which you can see in the background here, within the last year, which is super awesome because PACE also is able to measure chlorophyll and phytoplankton. And so I would love to kind of compare the data that we get from PACE with the data that I received from the MODIS instrument on NASA's Aqua satellite. And kind of to circle back to why this work is important, so like I mentioned earlier, climate change is only getting worse, and with climate change we're seeing more fires in California, and those fires are becoming more severe, and it's really important to know what impacts those fires are going to have, not only on us, but on our ocean's coast as well. As well as phytoplankton are hugely important. They are the bottom of the food chain, so small fish rely on the phytoplankton to be able to survive, and obviously the larger fish rely on the small fish, and so without phytoplankton our fisheries would most likely collapse. As well as harmful algal blooms, we need to be able to predict and know when and where those are going to happen, because those do have negative effects not only on us, but also on the marine ecosystems that we rely on. And with that, I would just like to acknowledge specifically Megan Ward-Baranier and Dr. Dan Sousa for being an amazing help this past couple weeks of my research, as well as the entire land group. And I would also like to thank everybody else that was able to make this research happen. I had an amazing time, and thank you. I'm happy to take any questions.
Any questions for Ben?
Yes.
Great talk. You've taken on a really challenging problem. The chlorophyll algorithm detects changes in blue and green light. Have you thought about how the processes of runoff and, for example, settling ash, et cetera, might affect our ability to measure chlorophyll from satellite?
I have thought about it a little bit. So wildfires that can affect the coast in multiple ways. Not only can they deliver nutrients, or they can affect phytoplankton in multiple ways. Smoke plumes can block sunlight, and phytoplankton needs sunlight to be able to photosynthesize. So I have also thought about the fact that there were some studies looking at the turbidity of waters after that and seeing how that affected phytoplankton. So I think that would be definitely really interesting to look into further to see that specific impact, and maybe seeing if we can quantify that turbidity and maybe add that to the model to see the impacts of that. So thank you, that was a great question. Yes.
Following up on that, you had a great point about pace,
Mm-hmm.
maybe being able to shed some more light on this topic. Do you have any thoughts on what it might be some of the exciting opportunities if you were, say you were doing your project and it was a few years later than today, and being able to use hyperspectral observations, how might it have changed the way you think about your project?
So I haven't done too much research into PACE. I was looking into it a little bit a couple days ago. I really wanted to use PACE. I was really excited when we were learning about PACE in the first couple of weeks of presentations. We were learning all about the different satellites that NASA has put into orbit. So I'm not sure exactly what the differences are that PACE would be able to deliver to me, but I was definitely disappointed when I found out that PACE has only been in the air for less than a year, that I wouldn't be able to, there's no data on those previous wildfires that I use in this data. So I'm hoping to be able to continue this and either switch out and use PACE, or maybe somehow integrate PACE into this research.
Thanks. Great
Yeah,
job.
thank you. Yeah, Ben?
Does your model be used to like look at something different, like with the streams, like instead of the length, like maybe like ecosystem characteristics?
That's a great question. So it depends, I think. So the model I used was a regression model, and so basically that means that it predicts based on continuous numerical data. So if we could find a way to quantitatively, if we could find a way to create that data that you're talking about, like in quantitative numbers, then most likely you could add it to that model and use it to help further predict the chlorophyll concentrations. Great question. Dom?
I know you said that the region is contributing to the difference in the algae blooms between northern and southern California. Do you have an idea like what specifically part of the regions might make it differ from each other?
I do a little bit. So continuing this research, I would love to input a lot more data. So like I said, rain and wind. I think climate is probably the most apparent difference between like Northern California and Southern California. So if I was able to add like humidity, rain, winds, temperature, there's like a ton of different aspects you could look at. So that would be like my first idea, but I would definitely have to do more research to see like the differences in that. Maybe if there's differences along like, there's geographical differences like along the coast, whether it's like sandy beaches or coastal cliffs or stuff like that. But yeah, that's a great point you bring up.
Are there any other questions? All right.